to get started in here. Okay. So good morning. Good morning. This is our week 4. A lot of things to remind folks. Number 1, for this week, we have the lab, right? We have the lab this Wednesday. Let me bring up the thing in here. Where's the syllabus? So based on our course schedule, for week 4, we have a lab, lab 3, right? This week. I believe lab 3 is about, I can't remember exactly what lab 3 is about. I think it should be about image processing. Yes, it is. The exact problems, I think, is about geometry. Now, let me double check. Okay. See, lab 3. Sorry. This one, lab 3 is about tuples. Lab 4 is about image processing. So in here, this no, that was PA. Lab 3. Let me check. Yeah, lab 3 is about tuples in here. And make sure you work on the lab this Wednesday. Okay. And then finish the quiz. For PA4, you can see PA4 already. It was released yesterday. PA4 is about flipping pictures, right? So you're gonna flip a certain region of a picture, okay, in here. So make sure that you work on these 2 functions, flip vertical and check validity, okay. PA4, I would say, can be a little bit tricky because you're gonna see this PA4, you have to be very careful with off by 1 errors. Okay, you have to be very careful on that. Are there any questions about this part? All right. So let's look at and then at the end of this week we have a quiz. So make sure you finish the quiz as well. Okay. Let me see. There's one question in here. Would it be similar to what you did last week during lecture for this PA? Similar, right? We learned about how to flip a picture, but that's the entire picture. What you'll be doing is you're gonna carve out a region from the picture and flip that small region. It's gonna be like this for PA4. So you say, okay, flip this region. You're gonna just flip this region, not the entire picture. So you have to work on geometry a little bit, and that track validity function would basically allow you to verify if this region is legitimate region or not. But that's about it. Okay. Any other questions? So this week is a full week. We have PA, we have lab, we have a quiz. Okay. Now for the material today, we will we'll try to finish picture manipulation. I don't think we can. We can't finish everything about steganography, but definitely we'll get started with steganography. Okay. So the plan for today is we'll do background substitution and get started with steganography. Okay. There's another question. Can we release the grid scope quiz 3? Let me check. Okay, so week 3 quiz. Look at the setting. Show answers. Okay, you should be able to see the answers on Grid Scope now. All right. Um, any other questions, comments before we get started in here? So this is the final stretch of the summer session. So make sure you don't drop the ball on any of the assessments. Okay. And then this week we have the last quiz, so there is no quiz next week. We do have a lab, we do have a PA next week, but there is no quiz next week. So just make sure you look at the syllabus properly. Okay, look at the schedule of what is in here. Okay, so we have quiz 4, PA 4, lab 3. Okay, all righty. If there are no other questions, we'll get started in here. Okay. So last time we talked about processing a picture using some sort of geometry, like mirror picture, flip a picture, and we talk about off by one errors, right, that we should avoid. Today we'll be looking at some more nuanced processing of pictures. Number one is to change some background. A lot of times, what we did up until today is we write a nested for loop, right? We say we specify the range for I, we specify the range for J. Basically, this would create a rectangular area. If you think about the mirroring, right? Our nested for loop basically created this rectangular area on one side of the picture, and then we copy it to somewhere else, right? You can also do other manipulations. Like, for example, if you think about a filter on a picture, we say, well, the entire area is like this. So the rectangular area we specified, we process every pixel in the same way. That has been what we did. But up until today, we didn't do anything special in this area. So what if the area that I want to fix, I want to change, is irregular with respect to shape? So for example, I have this red caterpillar. I want to change the caterpillar from red into black. How do I do it? Right? If you look at this kid, in fact, I think she's the son of one of the faculty, who is a faculty at Michigan, okay, University of Michigan. He kind of pioneered this media computing idea. Her name is Jenny. So if you look at the eyes are red, right? So it's red eye. So the problem is, if I want to remove the red eye, what should I do? As you can see, the region that I want to change is not necessarily a rectangular shape, right? So I shouldn't do the same thing for every pixel in the picture. If we are looking at a situation like this, what we can do is we can try to look at the picture and follow this idea. Okay. So we will pick a region to go through, and this region will be a rectangular region because there's no way we can specify, for example, a circular region, but the math will be too complicated. So we're not gonna do that. We'll still use a rectangular region. We'll go through it. But inside this region, we are not gonna say, for each of the pictures, I'm gonna do something. For each of the pixels, I will do something. I will look at individual pixels and look at the color of that pixel. If the color satisfies certain requirement, in here is like red. If it's red, I would change that pixel's color from red into something else. And that is the idea of changing the background of something. Okay. Are there any questions in here? So let's look at the caterpillar. Okay, let's look at the caterpillar, and then we're gonna write the code to change the color of the caterpillar. Okay. And also we'll try to write the code to change the red eye of this picture. Now, what's the color of this caterpillar? Can we have a vote? What do you think the color is? Okay, let's vote on this one. All right, we'll stop the voting here. A lot of us said, hey, it's red, right? It's pure red. Let's take a look at it. Okay, so I do have that picture in here. Let me see, where is that picture? Caterpillar. Let's see. I'm gonna open the caterpillar using paint. Okay, so this is the caterpillar picture, and I can sample a color. So let's just sample it, and then I can look at the RGB. Where's the RGB? You can look at it in here. If you look at the red, it's 25400. That's the red, which is different from 25500, right? You say, okay, maybe it's just that pixel I sampled. If I sample another red in here, if you look at it, it's 25511. So what I want to convey in here is this is red, right? It's almost identical to pure red, but in reality, we don't always see pure things, right? There is always some sort of fuzziness in here. So the correct answer to this one is it's probably very close to A, but there may be some variations. I just don't know the exact value, but it should be fairly close to 25500. Maybe it's 250 for red, maybe it's 5 for blue, it's 5 for green. It's possible, right? Because they're all red, and human eyes cannot tell the difference that much. And this is important when you try to change the picture. So this fuzziness. When you say, I want to change a red pixel, you cannot just say, I will only change pure red. If that's the case, we're in trouble. Okay. Any questions about this? Let's look at this function. So let's, I think we're trying to change the caterpillar in here to yellow. Okay. So we want to write this recolor function. Given the image, given the color I'm looking for, so this is like the color that I specified, and x min, x max, y min, y max is the region that I would use to specify the rectangular region. So it's going to change all the colors that are close to this color in this box between x max, x min, y max, y min into yellow. This is the yellow color. What should I fill in these blanks? You can see this coding challenge in this URL too. Let me give you the coding challenge for this one. Okay. So here it is. Okay. Can you finish this code by yourself? Okay. I'll give you some time. Give me a vote once you think you you have the answers. Either you can write it on add stem, or you just list out the statements in here. Either way is fine. Okay. No one has voted in yet. 2 minutes in. Right. Um, look at this is getting us, right? I didn't see anyone voted in. It's 3 minutes in. Um, let's write this together. How about that? I think this is maybe this is fairly tricky. Okay. So let's write this code in here. So I have the caterpillar. I have the caterpillar in here. And then what I would do is I would try to change the caterpillar into um, from red into yellow, whatever it is. Okay. So the first thing I want to know is like I need to write my nested for loop. Remember, X is the horizontal, that's the column. Y is the vertical, that's the rows. So you say for I in range of Y min, Y max. We are assuming it includes Y min, it doesn't include Y max. Okay. If you look at Y min is 0, Y max is H when I call the function. For J in range of X min, X max, right? This is what we have. Now I need to look at the color, right? So let's say RGB, I need to extract this color, IJ, right? Now I need to check, is this RGB close to color? If I simply do this, if um, R is the same as color 0 and G is the same as color 1 and B is the same as color 2. If this is what I'm doing, this is an exact match. I would say image IJ equals to, let me use black. I think it's easier for us to see kind of the contrast. And that's it. Right, so I can write this code and I would run it. Python change.py. I do have the new cat in here. If you look at this new caterpillar, it's not perfect, right? So some of it is changed into black. Those are the exact 254 but a big chunk of it is not, it may still red, it's not black. So what I would do is I probably would try to introduce some fuzziness, which means if I say R is close to color 0, I would do it. How do I introduce fuzziness? You can do this. If R minus color 0, you take the absolute value, you say it's less than the threshold. If their difference is less than 10, for example. Similarly for G, and you can adjust the threshold for different color channels. For G is, I'm going to just use the same thing, but you don't have to. I'm using 10 as the cutoff. Similarly for B, If this is the case, I will make it black. Right, so yeah, this is the fuzziness idea. If R is close to the corresponding redness of the color I'm looking for, so if I now run it, let's look at new caterpillar. Oh, it's better now, right? It's much better than before. There's still something around here that is not black. So maybe I can introduce the fuzziness a little bit more. I'll say maybe 10 is not good enough. I'll say this is like 80. And maybe this is, let me see. So a lot of times it's useful if you look at the redness around the region that didn't get changed. Let's see. Looks like it's the boundaries. Let's take a look at the boundaries. Oh, that's not. Let's see. 253.02. That one should have been changed. Let's sample something that is around the edge. 165.03. 165.03, that's also red, so which means it looks like this thing should be much bigger, maybe 120. And for red, for green and blue, maybe I can maintain the smaller cutoff or run it again. Let's close a new cat. And now it looks better. You see, there are minimum number of red left over. Um, so it's not going to be perfect, but it give me pretty nice effect in here. Any questions? For adjusting the threshold, you see, this is when the cutoff is 10. This is when the cutoff is 80. You can see the difference, right? Any questions in here? So that's the first thing for caterpillar. Now I also have this Jenny red, right? I want to take care of her eye in here, and I have to know what is the redness around this red eye in here. So let's open it up. Do I have Jenny red? I don't. So let me save this picture. Save it on my test in here. Let me open it up. Okay. So Jenny red, open with paint. All right. So let's sample the color of the eye region. Look at it. It's 164, 24, 37, around this number. So when I try to call the function, it's 164, 24, 37, and it should be Jenny red. And if I say, okay, whenever I see something like this, I would try to change it. I will start with a smaller cutoff, let's say 40. Okay. So 40 in general is a good cutoff because in real life, these colors, they vary a lot. Okay. Would you say this code would work in here? A is gonna work, B it won't. Would this code work? There's a new Jenny. Can I have a vote in here? Would this work? A is gonna be yes. B is no. What would you say? Can you vote on this one? I changed the color for Jenny, and I'm going through this. Would this code work? To change the red eye into black eye, right? The eye color will be black now. All right. Um, a lot of us said no, right? I think the answer is no, right? This won't work. You can run it. And the reason is pretty simple. If you look at new Jenny, well, the shirt is red too, right? And there's this lantern that is red, but I mean, we do see that her eyes are now mostly black, but her shirt got messed up too in here, right? So our region that we specified was the entire picture, and that's not good, right? We want to specify her eye region in this region. So you got to figure out what is the region that you want to specify in here. So, okay, how do I know the eye region? You can kind of use paint in here. So how about the height? Up over here, in the lower left corner of paint, you can see the coordinate. This is X. So as you move it, you see the number changes. So this is row 110. This is row, sorry, this is row 89 to 115, 89 to 115. So the row number should be 89 to 115. That's 80 to 120, just to give ourselves some wiggle room. And how about the column number? The column number goes from 107 to 200, around that. So I say from 100 to 200. By doing this, I'm really carving out the region around her eyes, right? So if I do this, I run the code, you'll see Jenny, new Jenny. I need to close this. You'll see the difference between this picture and that picture. You see the shirt before was messed up, now it's not. Now only the eye regions are changed. Okay. Any questions? As you can see, there are still red hues in here. If you really want to change it to give you a kind of even better effect, you can maybe adjust the threshold on red a little bit more, and then try it. Right, so let me close new Jenny and open it up. Maybe that's even better. Maybe there are fewer red hues in here. But as you can see, there is a problem, right? If your cutoff is too big, her eyelid in this region are not marked as black. So before there was not, but now there is. So there are also some artifacts in here. So this cutoff is kind of very subjective, right? You have to think about how to pick the best cutoff. Maybe 80 is too big. We can adjust, right? So it's up to you to decide what to do. I think 40 probably something we can live with. There is a question how to examine the coordinates. There are different software you can use it. I think for Mac, there's this thing called examine picture info or something that is kind of that comes with Mac. For Windows, like what I have, if you open it up with Paint, if you just move your cursor around in here, you will see the lower left corner start to show the coordinates of the pixels. So that's what the first one is the column number. The second one is the row number. So if I'm looking at column number from 106 all the way, if I move to the right side is 206. And the row number is from here is like 106 to, sorry, this is 80, 80 to 90 all the way to 115. So you are using the corner in here. This is the region that you can read the position of your mouse as you move across this picture in Paint. That would give you some information about the location. Okay. Any questions? All right. So this is the how to change the background here. Okay, how to change the background. Let's go back here. I think we finished this coding challenge. Okay. So you can't use the exact thing. If you use the exact matching, then nothing would happen, or like very few things, very few pixels will be changed. Okay. All right. So that's the first exercise, how to change the background. Are there any questions about that? Okay. Another thing that you can do is I used to have some pictures with a traveling dog, for example. A lot of times, for example, let's just use the caterpillar, right? Caterpillar is simple enough. Let's do it in here. So this caterpillar is sitting on a green leaf, right? I say, okay, I don't like it. I don't want the caterpillar to sit on the green leaf. I want the caterpillar to sit on someone's picture. How do I do it? I say, I want caterpillar to sit on Jenny. Right, so it's a weird request, but it is what it is. So I want to copy this Jenny's picture into the caterpillar's green leaf. This is called background substitution, and this is kind of how the green screen works in the movie industry. Right? You have this uniform color, and then whenever the software sees a green color, it's gonna change it into another pixel from another picture. Right? So that's something that in fact we can try to do. Okay. Let's create another challenge. Let's call this I'll say background change two pictures. Right? So how do I do this? Let me upload a few things. Okay. I will upload Jenny's picture. Um, Jenny, I will upload Caterpillar. I will upload the CSE 8A. Let me upload it. Okay. So for 8A, let's see. Where is my let's see, notes. I don't see 8A image library. So I think I have to download it. Okay, so I'll create a file. Let's do this. CSE 8A image dot lib dot py. I think that's the name of the file, if I'm not mistaken. Um, Nonetheless, okay. Let me copy down what we had in there. So from the previous challenge, and this idea just came to me. So CSE 8A image, just copy it here. Okay. All right. So let's change the caterpillar's background into Jenny. So the caterpillar is sitting on top of this picture instead of a leaf, right? How do I do this? Let's work on this together. Okay. Let's write a new file, say bgchange.py. Okay, background change. So from CSE data image import asterisk. And I'll just load, for example, image. I'll call this the front image equals to image load image. I'll load in caterpillar .jpg. This is the front image. The the background equals to image load image. Jenny red.jpg. So we'll try to copy the region from Jenny into the caterpillar. Let's look at the dimensions. I think these two pictures are similar dimensions, if I'm not mistaken. In general, we would prefer the background picture to be a little bit bigger than the foreground. Where's Jenny in here? Let's see. What's the dimension? It's 300 by 266. How about caterpillar? 329 by 150. It looks like Jenny is not big enough. So how about we use engineering bear? So the caterpillar will not sit on Jenny, it will sit on engineering bear. Let's upload the bear. I think the bear is definitely bigger. Where is bear? Okay, there we go. I'll remove Jenny. Okay, so let me also upload it in here. It's easier for us to see. I'll remove Jenny. It's too small. Jenny is too small. Picture size. Okay. So I will change this one to be the bear.jpg. The bear is bigger than caterpillar for sure, with respect to picture size. Now, how do I change it? The idea is I will go through the caterpillar. When I see a green pixel, I would copy the corresponding pixel from the bear into the region of the caterpillar. Okay. So this is how it goes. I would say h equals to the height of the front picture. W equals to the width of the front picture. So I would go through the caterpillar, roughly speaking. Right? So I would say for I in range of the height, for J in range of the width. And what I will do is I will try to copy in when I see a certain color. Can you all do this? I should give you some time to try to do this. Can you all try to write out what I should do in here, in this for loop? Okay. So give you a few minutes. Can you try to solve it yourself? If you're able to solve it, give me a vote. Okay. So you can see the link to the coding challenge in the Zoom chat. And this is like how green screen works in the movies. It just has a faster processor, so it can process frames of movies very quickly. Give this a shot. I want the caterpillar to be sitting on top of the bear, roughly speaking, if possible. Yeah. How can I achieve this goal? Try this. No one has voted in yet, but take your time. Okay. No one has been able to get this one yet. Looks like this. I should give you more time. I think we may have time today. So practice, use this opportunity to practice. Okay. No one has voted in yet. Interesting. 4 minutes in. Okay. All right. So I think due to time, we should get started working on this together. Okay. Um, I don't think anyone were able to solve it during the 5 minute period. So in here, what I will do is I need to check what is the color that I'm seeing from the caterpillar. Is this green, right? So you probably need to measure green a little bit. So what green are we looking at? Green is like 1 to 55.0. So pretty nice green, right? So I would say if ABS R minus 250, R is less than 10 and G ABS G minus 255 is less than 10 and ABS of the B is less than 10. Probably you don't need ABS for here, but it's okay, right? So I see a green. If I see green, I would make sure that this front IJ equals to the corresponding background picture of the bear. That's what I'll be doing. And that's it. So this is the statement. I can save image. I say the front picture is changed. I'll say new cat.jpg. I'll call this cat bear.jpg. So let's write this. Let us run it. Python bg change.py. We have the cat bear in here. As you can see, the bear is now as served as the background of the caterpillar. Okay, pretty nice, pretty interesting, right? You can definitely put someone's face in there. That's fine too. Okay. Any questions about this idea? If you see a green, you just let the other pixels RGB to be assigned in here. So this is how you merge one picture into the other picture. All right. I think let's take a break in here. And let's take a break. We'll come back at 12, and then we'll continue our discussion in here. All right. So let's take a break. Take a break. Okay. Come back 12. All right, everyone, let's come back. Let's finish up background change, and then we'll move on to steganography. Okay. So, before the break, we were looking at background change, and we say, okay, we can put one picture's pixel to another picture, right? The thing here is, if you look at the cat bear, the bear is right at this spot. In fact, you can also give it some sort of offset. For example, I wanted the bear to move to the left side a little bit more. Then what you can do is you can say, okay, instead of at the exact same spot between front and the back, I would say I'll give you 10 more. If I run this, there's going to be a small offset that probably would give me a small variation. This is the original cat bear, right? The bear is kind of between these two segments. If I close it and look at this is not what I'm looking for. This one, if I look at the cat bear again, you may see a small change. Maybe 10 pixels is hard to see. 10 pixels are too hard to see. Let's look at maybe a slightly bigger one. Okay, so 50. But you are running the risk. If this offset is too big, you may be out of bound on this background picture. So in general, we would prefer the background picture to be bigger, sometimes a lot bigger. You see, it's out of range. So our background picture is too small. This bear compared with the caterpillar. Maybe I can, you know what, it's not worth searching for another thing, but let's see. 50 is too big. Let's say 20. This is probably going to be okay. Okay. So if you look at the, let me close the other pictures. Close tabs to the right. Let me first open up cat bear. This is what the old cat bear is about. Okay. So you can, I think it's already changed if you look at it. So the bear used to be the head is in there, but now the head is underneath the caterpillar. If I close it and open up again, maybe there's another change. Maybe it's already updated. I think it's already updated in here. So the bear head is now behind the caterpillar. Okay, so this is something interesting, right? The other thing that you can also do, which is also a pretty interesting fact, is to say, I want to mash two pictures together. In other words, you can create some sort of ghost effect, right? So you may have like you may have caterpillar. Okay, you have the caterpillar, you have the bear. And I wanted the caterpillar to appear in front of the bear while not blocking everything from the bear. You see what I mean? So it's like there's a ghost caterpillar in this picture. That's another special effect that we can try. Okay. So how do we do that? It's very similar like this one. I'll just do this. I don't even have to judge based on the color. Maybe I can. Excuse me. So basically I have right now I'm detecting green in here, right? If it's green, I don't copy in. So I'll add a knot of this whole thing. Right? If it's not green, what I will do is I would mash the caterpillar onto the bear. And also, let's see, and it's not white. For example, I'll say R ABS R minus 255 is less than 10, and ABS G minus 255 is less than 10, and ABS B minus 255 is less than 10. In other words, as long as it's not green, not white, I'm looking at that caterpillar. I will match this caterpillar to the bear. If I'm doing this, I probably want to go through the background picture, and I would match the corresponding caterpillar pixel in there. So I would look at the caterpillar, right? So if the caterpillar is not red, I will put it into the bear. So I'll say image ij. You know what? I think this effect just came to my mind. I should probably still go through the front picture because the front picture is smaller. If I'm not careful, I may be out of bounding here. So I look at this one. If it's not green or white, I would say BG's IJ equals to BGIJ times 0.4 plus front IJ times 0.6. So I'm kind of mixing these RGBs together, and I typecast it into an int. And let's save the background picture. Let's see if the tuples can allow us to do math in here. Okay, let's run it. So it's the indentation. Okay, so let's not do that. Run again. Yeah, I don't think you can multiply it in this way. Looks like we have to do the RGB the old school way. So I already have the RGB in here for the front. I say R1, G1, B1 equals to the BGIJ. And I would do this thing. So it's R plus times 0.4 plus R1 times 0.6. That's the red. And then I would do I think I may, let me see. I think we should be able to do this. Hold on. I think it's the, you know what? Let's just forget about it here. And then B times 0.4 plus B1 times 0.6 are G. So this is G. And then B, right? B times 0.4 plus B1 times 0.6. You just have to make sure you typecast this into an int, typecast this into an int before you make them a tuple. Also typecast this part into an int. And this whole thing, they form a tuple, and we can save it like this one. Okay, I think it should work. So the argument is I look at the front picture, which is the caterpillar. If it's not green and is not white, let me see. Should I say or in here? I think it's or, logic wise. You just have to be very careful. Then you should mix those two pictures together. All right, so let's look at our cat bear. Let's not delete it. Let's look at cat bear. I think Hey, if you look at this one, so the caterpillar is on top of the bear, but the background didn't work, right? If you look at it, the green is still there, the white is still there. Um, let's see why. Uh, I think this logic was not working. So this is not green. This is not white. So if it's green or white, we take a not. Maybe this is and. See, the logic, sometimes I would make mistakes on that logic. Let's try it again. Cat bear, close it. I think now it seems to be working better. If you look at this picture, the caterpillar is on top of the bear, although like these are the circles, this is a line, but the green and the white are not copied in, and they're mushed together. So it's not like the caterpillar is totally covering the bear. And the way that which one is more obvious, it depends on how you mixed them together. Like right now it's 40% foreground, 60% background. That's kind of what I have. Um, if you want it to be lighter, you can maybe 2080. So the caterpillar would be lighter. Okay. All right. All right. My phone started to ring in here. And this is 8020, right? So if you run this code, the caterpillar would be lighter compared with before. If you compare this one with the previous one, you can see the difference, right? This is the darker caterpillar. This is the lighter caterpillar. It's like there's a ghost caterpillar walking around, right? Where are these numbers coming from again? What numbers? What are the numbers we are referring to? There is a question. Oh, dot two. So these ones, if you think about, we're trying to mix two pixels together, right? So this redness is the caterpillars are, this R1 is the bear's red component. We're mixing them together, so it's just like 100%. 20% is for caterpillar, 80% is for bear. So the bear is more obvious, and you can adjust them. These are subjective numbers that you can use to adjust so you can achieve the desired effect. Okay. Any questions about this? All right, so we are done with background change. Okay, so we talked about quite a few effects in here. We talk about change a certain color in the picture. You have to allow fuzziness. We also talk about mixing two pictures together, right? They follow the same idea. You specify a region and you look at the color in that region and decide what to do. Okay, that is the idea. Are there any questions before we move on from this topic? If there are no questions, let's vote on this one. Okay. So I have this code, um, and I have this function called copy region to new. And this is what I'm doing, and these are the function calls. What would you say this code will do? Can you vote in, please? Take your time, look at the code, analyze it, and decide what to do. which one is the right answer. I'll give you 2 to 3 minutes on this one. It's a little bit tricky. Vote in. Okay. Two of us voted in. Okay. What does this code do? It says copy region to new. Right. Out of the three people who voted in currently, all the three choices are different. This is more about the memory models. Okay. All right. So out of the four people who voted in, all of us are voting for the different answers. Right. So let's work on this together. How do you access this thing? So you start from the memory model, right? You're gonna realize what's gonna happen here. First thing, pick goes to load picture arc.jpg, right? This is the first line we'll analyze. So pick is now pointing to a picture object, is arc, right? And then I'm calling this function copy region to new. I pass in the pick. In other words, when I call this function image, this is the stack frame of the global stack frame. And then inside copy function, I have this image. Image is pointing to the same object in here. Okay. And then RS would be 10. And then the other CS would be 30. And then RT would be 50. CT would be 50. So row source, column source, row target, column target. And then I get the width and height of the picture. And then I created a new image of the same dimension as this arc. So this is a new image and everything is black in here. What we did is for a block of 100 by 100, I copied in from the image from here, row plus row source, column from column source. In other words, we grabbed the 100 by 100 region from this region and copied it somewhere over there. So if there's an arc in here, and this is the region we're copying, and this arc will be here. This is the 100 by 100 block that we'll copy. And then once we are done, we are done. So if we say image, we save image, it's still gonna be this arc. Sorry, I don't even have the image in here. But these ones, in fact, we'll see errors. So how come there's error? Once I'm done with the function call, everything in here will be destroyed. There's no image, there's no new image, there's only pick. So this one would in fact generate an error. The last one won't generate an error, but the first two statements in here, these two, they will give you error because I don't have IMG in the global frame. I don't have the new image in the global frame. So whoever voted for A, you got this one correct. Any questions about this part? So it's because of this IMG new image, they don't exist in the global frame. The follow-up question is, if I have a return statement here, I say return new image in here. Nothing else changes in here. What would you say the answer will be? The same choices, right? So A, B, C, D, E. If I add the return image, what would you say the answer is? All right, so a lot of us now are voting for C. So, okay, if I return new image, it's gonna work. Unfortunately, the answer is still no. The answer is still no. Because if you're saving image, you still don't have the image. You don't have that, right? And even if you say return new image, you are not returning this variable from here to there. You're just returning this arrow. And I didn't capture that arrow. So it's still gonna be an error. No difference. No difference. Okay. So this code will give you error, even if you add the return new image. Any questions? When you return something from a function, you are not handing back a variable. You are handing back a value. Everything in here is passed by value. This is not only good for Python, but for any language. You're just passing the values around. Okay. You're not moving the variables across different frames. We're not. Okay. Any questions about this part? This can be fairly confusing. Okay. All right. So we are done with basic image processing. Now we're moving into the topic of steganography. Okay, steganography. Um, let's see. I think I put in some basic stuff in here about steganography. Um, let us just cover this part today, and then we'll call it today. Okay. So, what is steganography? Steganography is one way for you to hide plain information right in front of the observers, but they don't know. We're hiding the information. Okay. And the user, the receiver who knows the trick will be able to decipher what was being sent. And that is the goal of steganography. Okay. Um, so if you look at this sentence, right? What does this sentence say? Kathy saw 8 airplanes penetrate skies aloft. 7 really could only keep straight. It's a silly sentence, right? What information is hiding? If you look at it, it really doesn't make much sense, right? But if you look at the first letter, right? So if you look at CSE 8A, PSA 7 rocks. In fact, PSA 7, PA 7 in the regular quarter is about steganography. For us, it's the last assignment in here, the PA 5. But the idea is if you just read the sentence, it really doesn't convey a ton of information. But if you know where to look for it, then uh, you can see what information is hiding there. That is steganography. And in the context of what we are doing in this class, we're not trying to hide sentences in an article. Right? In World War II, a lot of times people would like the spies, they would publish articles on New York Times or in a different newspaper, and the observer would be able to kind of detect what information is being sent to the public, but if they decipher it, you're gonna see a secret message. I think from NYC, I think World War II. I think there was an article, steganography, steganography. I think there was an article, New York. There was um, there was an article from New York City, like New York Times, that was using the steganography. I think that I'm just looking. This is a research paper from, but that's not what I'm looking for. I can't remember the exact article, but in World War II, in New York Times, I think this says this Persian is like a ship would sail from New York on a certain date, and it was kind of embedded uh, in a New York Times article. I remember. I can't remember this one. So um, nonetheless, okay. I don't think we should spend time looking for that article, but this one would give us the idea. Okay. For our class, what we care the most is the following. We want to hide a picture inside another picture, and no one can see it. In other words, it's like just look at an ordinary picture, but another picture's information is embedded in there. And that's your job for I think PA5. Okay. So let's look at this one. Um, I have two blue pixels. These are two blue pixels. I don't know if you all can see the difference. Well, I can't see any difference between these two blue blocks. They're about the same. They're about the same. Okay. But they have different RGB values. The first one is 395611. The second one is 3759 100. In other words, their RGB values changed just a little bit. For human eyes, we can't see any difference. Even if you are an excellent artist, most likely you won't be able to see the nuanced difference in here. And that's the thing we want to exploit. In other words, we'll take advantage of this thing. In other words, human eyes are not very sensitive. If I change the pixels of a picture just a little bit, hopefully that would not give any hint to the human being to say, okay, there's something changed. And those variations can be used to hide the information about another picture. That's kind of the idea, right? Obviously, we're learning this in 8A not because we want to learn steganography, although it's fairly cool, but it's more about how to process pictures. And in here, we have to think about things in the binary domain. Okay. So we're looking at binary numbers now. I think it's important that if you're taking a CS class, you would be comfortable with the binary numbers. So the goal for today is to get started with binary numbers, and then we will try to show you that a small variation of a picture's pixels would not cause any observable differences when human view those pictures. Okay. So let's first start with binary domain. What is a binary number? Binary number is in contrast to decimal numbers. Decimal numbers are base 10. We know that. Binary numbers are base 2. Right. So for decimal numbers, you have 0 to 9 as digits. For binary numbers, you only have two digits, two possible digits, 0 and 1. Right? So binary number is made of 0 and 1s. There are just two different ways to represent the same number. So we're basically looking at the same number from a different angle. That's what we're doing here. Okay. Let's look at decimal first. So if I have this number, we know it's 3,878. We know this. And the reason we can read this out is we know that each position, this is a positional number system. Each position would have a different weight. So 8 has a weight of 10 to the power of 0. 7 has a weight of 10 to the power of 1. This is 10 to the power of 2. This is 10 to the power of 3. Okay. So that's what we have. So you can say this is 3,678. Right? So that's how you read out the numbers. So the position of the digit would matter. So are for binary. For binary, if you look at the binary number, the last digit has a weight of 2 to the power of 0. This is 2 to the power of 1, and then this is 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. So each digit would have a different weight. It's always from the rightmost, the powers of 0, right? 0, the 0th power, and then the first power, second power, and go on. So we are basically trying to look at the number from a different format. We call this the binary format. Okay. Any questions about this part? What is a binary number? Binary number is just 1 zeros. Okay. So what we can do is we can convert between binary and decimal. Okay, that's what we can do. For example, if you say I have a 39 in decimal, how do I convert it into binary? I'll first show you how to do it by hand, and then how to do it in Python. Okay, this kind of conversion, is it useful? I mean, it's important that you know how to do this by hand, but a lot of times no one would do it by hand because if you have a calculator, it can do it for you. But since we are learning this, we're gonna do it a couple of times just to practice. Okay. So for example, we say 39, how to convert it into binary. You do the long division. You divide 39 by 2, you write the quotient over here, write the remainder over there on the right side. And you keep doing the division until the quotient becomes 0. So 39 divided by 2, quotient is 19 with a remainder of 1. 19 divided by 2, you get a 9 with the remainder of 1. 9 divided by 2, quotient is 4, remainder 1. 4 divided by 2, you get a 2. There's no remainder, remainder is 0. 2 divided by 2, quotient is 1, no remainder. 1 divided by 2. If you are doing integer division, 1 divided by 2, the quotient will be 0 with the remainder of 1. Once the quotient becomes 0, you stop. You read it backward. So the binary representation of 39 is 1, 0, 0, 1, 1, 1. That's what we have in here. Any questions about this? That's the binary representation of the same number. Okay. Inside all the machines, every number is stored as a binary number. They're not stored as decimal. For humans, we use decimal. And when you say, I have a number, I print it out, it print out decimal. It's just machines that are trying to cater to humans. Right? The machine can easily spit out a binary number, but it will be hard for humans to understand what that number really represents. So the machines would convert a binary into a decimal and show it to us. But inside all the machines, everything is binary. The reason why we have binary devices is not because it's cool or it's fancy. It's just because these devices are cheaper to make and they are pretty stable. And that's why. So it's due to basically economic reasons. You can make machines that stores physically like decimal numbers, but those machines will be easier to fail and also more expensive to manufacture. So why would people do that, right? So any questions of how to convert a decimal number into binary? All right. Can I ask you all, I'll give you some time, either convert 56 or 11 into binary. You can pick either one. Okay. And then do the conversion by hand. Give me a vote once you're done converting. Okay. So you can pick either 56 or 11. You don't have to do both. Do this by hand. You only do it once, right? You will get the idea. It's not rocket science. And I don't recommend you do this all the time, right? But it's just you know how to do it. Right, two of us are done. Let's work on this together. I'll pick 56 again. Right, 56 divided by 2 is 28, remainder 0. Divided by 2, 14, remainder 0. 14 divided by 2, 7, remainder 0. 7 divided by 2 is 3, remainder 1. 3 divided by 2, quotient is 1, remainder is 1. And 1 divided by 2 is easy. So the whole thing for 555 is 111000. Okay, so it's just the conversion. Okay. Now, how do I go backward? How do I go backward? Like if I have a decimal number, how can I get it back to decimal? The way you can do it is you can do the math. This is to the power of 0, to the power of 1, to the power of 2, and then this is to the power of 3, to the power of 4. The last one is to the power of 5. The issue in here is for these 0 digits, 0 times anything equal to 0. So what we do is 1 times 2 to the power of 5 is 32. 1 times 2 squared is 4. 1 times 2 is 2. 1 times 1 is 1. So this equals to 39. So you can easily use the weight of individual digits to give you this weighted sum of all the 1 positions. And then you get the corresponding decimal value. Any questions about this? All right. So another thing that we can do today is I'll show you how to convert, how to convert between binary and decimal in Python. Okay, so call this demo. Okay, so let me show you in here. I'll just open up Python in here. Okay. So I'll say, okay, if I have a 39, can you convert 39 into a binary number? All you need to do is to do this bin 39. Bin is a function. Isn't convert the number into binary for you. So it's 100111. That's 39. You say, what's the binary number equivalency of 56? That's the binary equivalency of 36. The 0b, we call this the prefix. It says this number is expressed in binary format. Without 0b, this one would be treated as 111,000 as a decimal. Just be careful. Okay. So given a decimal number, you can easily convert it into binary. Now, how about binary into decimal? You say I have 0b 111,000. If you prefix a number with 0b and you just write it out, it's gonna tell you, oh, this binary number is equivalent to 56 in decimal. That's what we have in here. Okay. Are there any questions? So you can easily convert between binary and decimal. Okay. I don't think bin function can give you a width. Let me see. Bin, I say 56 with 8. Yeah, I don't think you can say 8-bit binary number. You can't do that. If, for example, I say, okay, convert 56 into an 8-bit binary number, the only 6 bits in here. You just append 2 zeros on the left side. Don't append zeros on the right side. Okay. Are there any questions about this part? So this is binary to uh, decimal. Okay. What I really want you to see is it's just two different ways to look at it. And why do I have to convert from decimal into binary since they are the same? Because inside the machines, this is what it is stored like. And when we try to say we'll hide information um, in another picture, we have to change these numbers slightly, not a lot. If you change the number a lot, the change may be obvious. People may detect that. But if the change is fairly minimal, you can probably do it. You can probably do it. Okay. Using binary would allow you to make more nuanced changes in here. And that's why we have to look at the numbers in the binary format. Okay. Any questions in here? All right. Let's then look at a few uh, votes in here. So number one, if I have a value, okay, and I change the two least significant digits of the binary representation of that number, what is the maximum amount that I can change measured in decimal? In other words, if you say I have a binary number, assuming it's 8-bit, and I want to change the last 2 bits in here, what is the maximum amount of change I may have if I just modify the last 2 bits? Can we vote on this one, please? So what would you say? All right. So a lot of us saying B, 2. Okay. Let's you know what? Let's take a quick break. And we'll come back. I will show you how you can judge this. Okay. I think it's break time. Let's take a break until 1, and then we're gonna, in fact, it's not B, it's C. The difference will be 3. Okay. But break time. We'll come back and explain. Okay. Come back 1 o'clock, please. All right, everyone, let's come back and finish up the materials for today in 1 minute. Yeah. All right. So here are the rest of the topics for today. Okay. Let's look at this one. In here, the answer to this one, if you change the last two bits of the binary equivalency of a number, the impact would be at most 3, in fact. Okay. So why? Why is this the case? Let's look at this example. Okay. This is the previous example. Let's see. Okay. So for example, I have an 8-bit number. I'm just making up one, right? So I want you to focus on the last two bits. This is 1100, 1100. So this is 204 in decimal. If I change it to 01, that's 205. If I change it into 10, that's 206. If I change it into 11, it's 207. I want you to look at the last two bits with the first two bits being the same. The last two bits in here basically includes all the 4 possibilities, right? 0001, 1011. And you can see the binary, the decimal equivalency goes from 204 to 207. So the largest amount of change we may get is between 00 and 11. So the difference is at most 3. The difference is at most 3. And well, no matter what the first 6 bits are, the difference is always 3. For example, if I change the first 6 bits, I'll make them all ones. How about that? And the last 2 bits is 0, that's 252. If I have everything as all ones, including the last 2 bits, that's 255. So their difference is 3. The difference is 3. That's why if you simply modify the last 2 bits of a number, we call them the least significant bits, then the difference is 3. Any questions about this part? Okay. Now, another thing in here is, what if I change the 3 least significant digits, like the last 3 bits? What do you think the biggest change in here is? If 2 bits is 3, how about 3 bits? Can we vote in, please? It kind of expects you to know a little bit more about binary in here, right? So 2 bits, the maximum amount of change is 3. How about 3 bits? The last 3 bits. All right, out of the people who voted in here, I think more people voted for the right answer in here. It's a D. Okay, it's D. So what we have in here is, if you look at the last 3 bits, right, the minimum of the last 3 bits will be 0, 0, all the way to everything is being ones. So this is decimal 0, this is decimal 7. So the largest difference will be 7 in here, which is 2 to the power 3 minus 1. This is 2 to the power of 2 minus 1. So if you change the last 4 bits, for example, the maximum variation will be like 15. Okay. Any questions about this part? All right. So this is the changing the last few bits, right? So why do I care about the last few bits in here? If you look at these two blue pixels, right, that I've shown before, these are blue pixels. If you convert each of their RGBs into binary, this is the first blue block, this is the second blue block. You can see they are almost identical except the last 3 bits. So you may mess up the last 3 bits any way you want to. The argument is human eyes cannot see the difference. Cannot see the difference. And this is the kind of the feature we'll try to exploit when we try to do the steganography. Okay. Questions about this? Let's think about the colors and then I will show you why it probably doesn't matter. Okay. Excuse me. By default, RGB, we use 8 bits to represent red, 8 bits for green, 8 bits for blue. So that's, we call them 8-bit per color channel. The question is, how many unique colors can we represent by using 8-bit per channel? We have 3 channels in here. Can we do a vote? How to do the math? How many colors do we have? All right, it looks like we disagree with each other a lot on this one too. We'll stop the vote in here. Okay, we'll stop the vote. We disagree with each other if you look at the votes. Now, what's the right answer in here? So if you look at for red, since there are 8 bits, the pattern can go from all zeros, which means you have no red at all, to all ones, which is full-blown red. So this is decimal 0, this is decimal 255. So for red, you have 256 different unique colors. And then for green, you have 256. For blue, you have 256. And they can mix together. In other words, for each combination of red and green, you have 256 blue colors that can match to it. If you look at it, so it's altogether 256 times 256 times 256. That's 256 cubed number of colors. And this gives you about, I believe, so this is 2 to the power of 24, which is 2 to the power of 4 is 16. Around 16 million different colors. Can I explain that again? The math? So sure. So we know that there are 256 unique red. There is also 256 unique green, 256 unique blue, right? So the total number of colors they can all mix together is, you can say for each red, you have 256 choice. And then for each of the red, I can pick a green. for each of the green. And then for each of the red and green combination, I have a 256 choices for blue. So altogether, we're looking at 256 times 256 times 256, which is 256 cubed. If this is confusing, just imagine if you have a person, this person has 20 clothes, have 20 different kinds of pants, 20 different kinds of shoes. How many different appearances can this person have, right? So for each of the shirt, you have 20 choices for the for the pants, and then from that you also have 20 choices for shoes. So it's 20 times 20 times 20, like you have 8,000 different appearances. And here is the same thing. All right. Any other questions? Um, so 60 million is a pretty big number, right? So human eyes probably won't be able to tell all those 60 million colors apart from each other. Just like, for example, these two are two of those two out from those 60 million colors. So we can't tell these two apart, right? Now, what if I don't use 8 bits per color channel? I only use 2 bits per color. In other words, I use 2 bits to represent red, 2 bits to represent green, 2 bits to represent blue. How many unique colors? Um, sorry, in here, how many possible colors we have for each color channel? We're asking for each color channel. If I use 2 bits for red, how many levels of red can I have? So that's the question. Okay. So can we vote in, please? If I use 2 bits for red, how many different levels of red can I represent? All right. Um, let's look at the choice in here. So if you have 2 bits per color, 2 bits, which is 0, 0, 0, 1, 1, 0, 1, 1. So there are 4 colors per channel. How many unique colors is 4 times 4 times 4? You're looking at 64 unique colors. You're looking at 64 unique colors, but each channel only has 4 colors. So if you voted for C, that's right. If you say how many total colors, that's 64. Okay. D is incorrect. Are there any questions about this? You can think binary numbers are patterns. So how many unique patterns can you have with only 2 positions, and each position can be 0 or 1? So you can have 4 patterns. That's what it is. Okay. Now, for this one, if I use 2 bits per color channel, what this color should be in theory? What this color should be in theory? Um, can you vote in? So I only use 2 bits per color. So this is redness, this is green, this is blue. What would you say the color will be? All right, I think we're doing slightly better on this one. The answer will be pinkish, right? It should be pink because you have a lot of red. This is full-blown red, and then no green, some blue. So if you mix a lot of red with a little bit of blue, you're looking at some sort of red with a pinkish hue, something like that, right? But if I use them as the RGB value for Python, what would you say this color will be? Can we vote on this one, please? What should be the color? If I say, okay, a pixel has 110001 as in binary, what color will this be? All right, I think we are getting this one, right? So the answer would be black. So this pixel would be black because this is basically 301. And this is near black. It's not pure black, but it's basically very dark pixel. Let me show you the difference in here, and then I'll show you this is basically 40, no, not 14, 16 million color picture. This is a 64 color picture. I'll show you the difference between them. Okay. So let's look at these pictures in here. Let me create this one. I'll create this one. I'll say colors demo. Okay. So what we have in here is the following. I'll say demo.py. I need to create CSE 8A image dot py, and I believe I have to paste. Oh no, it's really clunky to do that, but let me copy this thing. Okay. So in this demo, let's create a picture from CSE 8A image import asterisk. Let's create an image with the pixel of 110001, right? So we'll say image equals to create image. I say 100 by 100 block, and each pixel is 0B11, 00B00, and 0B01. And I'll save this picture, save image. So image, I call this block.jpg. Right? So now let's run this code. Python demo.py. You will see this block, in fact, is a black block. Right? It's just because these values are so small in decimal. That's basically 3, 0, and 1. If you really want to say, I want this to be a kinkish thing, you want this 1, 1 to be on the left side of 8-bit, because in Python, everything by default is 8-bit. So if you say, I only have a 2-bit color picture, then you got to make sure that those 2 bits are the leading 2 bits, not the trailing 2 bits. You just have to make sure you append 6 zeros. Here's the same. 1, 2, 3, 4, 5, 6. If you now run this code, this block would be kind of pinkish red. Okay. Any questions about this part. Now let's look at some demos in here. Like, what's the difference between a 64 color picture and a 64? Sorry, like what's the difference between a 16 million color picture and a 64 color picture, right? So let me upload the bear here, bear.jpg. This is the bear, right? So this is a regular picture with 16 potential colors. Sorry, 16 million potential colors. And what I will do is I will do the following. I will load it. Okay. Load image. I say bear.jpg. I will load it. And now I'm ready to change it into a 64 color picture. How do I do that? What I will do is I will wipe clean the last 6 bits of every RGB for every pixel to be all zeros. I will only keep the first 2. And based on our deduction before, this picture would only have potentially 64 different colors. How do I wipe clean this region? We'll look at the details on Thursday, but the idea is we can, what's the easiest way? Then let me give you a quick deduction here. So hopefully it's gonna make sense. Okay. Let me open up Python here. So for example, I have 56, maybe like 134, just to be a bigger number in here. So I may have this number, right? If you look at it, I want to wipe clean everything in here. That's what I want to do. How do I do this? You can, if you look at the last 6 bits, to the power 7 is to the power of 7 is 100, to the power 7 is what? 128, right? So how do I get this 000110? You can do this. What's the binary equivalency of 134 mod 128? It's basically 110, as you can see in here, followed by those, like in the front, there are 3 zeros. Maybe I can give you a more concrete example. For example, I say 01, 111, 110. This is 126, right? So binary of 126. You can see the um the last 6 bits are these ones. And the last 6 bits are these ones. And how do I get the last 6 bits in here? You just use 126 mod 128. That would give you the last 6 bits. Let me see, the last 6. Am I miscounting it? To the power of 2, 3, 4, 5, 6. Oh, I only need to mod 64, sorry. This, because I'm looking at the last 6 bits, if you mod 64, that would give you the last 6 bits. Why is it the last 6? For example, if I'm looking for the last bit, what's the last bit of this number? You mod 2. So 126 mod 2 tells me, okay, the last bit of 126 is 0. If you say, what's the last bit of 127? It's 1. So it's going to tell you the last bit. If you say, okay, I want to know the last 2 bits of 126, you mod 4. If you look at the last 2 bits, it's 1, 0. If you want to know the last 3 bits, that's you mod 8, mod 16, mod 32, mod 64. So if you want to know the last few bits, you mod on the powers of 2. That's what you do. Okay, so mathematically it's gonna work out. So if I only say, okay, I want to keep the last, only want to keep the first 2 bits, wipe clean the last 6 bits, you can easily do this. You can do the following. So I'll say, what's the binary equivalency of 126? It's this thing, right? The last 6 positions are these ones. I said wipe them clean. I only want the one to be 0, 1 followed by 6 zeros. Then you can do this. 126 minus 126 mod 64. This would give me, I wipe clean the last 6 bit positions, only keeping the ones in the front. So you do a subtraction. So this thing minus that, you will get this result in here. So a quick demo in here, say h equals to the height of image, w equals to the width of image, for I in the range of h, for j range of w. So we will read in this RGB, and then we'll just change it. So we say image ij equals to r minus r mod 64, g minus g mod 64, b minus b mod 64. And now save this image. Save image. This image, I call this 64 color bear.jpg. Okay. So this would basically wipe clean the last 6 bits of each of the RGBs. And let's say, if we say Python demo.py, you look at the bear. This is the original bear. And this is the 64 color pair. If you look at this is the original one. This is the 64-bit. As you can see, the nuances are not there anymore, but I'm pretty sure we can still see this is a bear. This picture would only have 64 unique colors. Only 64 unique colors. So it's like painted using crayons, right? I think I was looking at a website from UCSD. This picture, if you look at the cloud in here, I was just here this morning, and I was thinking about what we'll do today. If you look at it, it looks like the 64-bit picture, right? So it's pretty cool. Any questions for you to kind of know the difference between a 64 color picture and 16 million color picture? This one is not as nice, but you can still tell it's a bear. Questions about this? Similarly for this one, this is a 16 million color, 8-bit per channel. This is 2-bit per channel. You can still see it's a swan, okay? In our steganography work, what we will be doing is we will be able to hide this picture in another picture, and then when we recover, we end up with something like this. In other words, we will lose some information, but the difference is pretty small, okay? You can still recognize the important things in there. Are there any questions? Okay. I think that's everything I've planned out for today. You probably had enough. When we come back on Thursday, we'll finish the steganography, and then we'll move on to dictionary. Um, and don't forget the lab tomorrow. Don't forget the quiz this Friday. Okay, so we can call it a day today, everyone. If